Today we are going to continue chapter 2. Last time we were discussing atoms and their structure. And we said that there were 3 subatomic particles: protons, neutrons, and electrons. And that's going to be important in today's discussion as well. So today we're going to start by talking about atomic numbers and mass numbers. So the atomic number of an atom is equal to the number of protons in the nucleus of the atom. And the atomic number is represented by the symbol Z. So Z is equal to the number of protons. And then the mass number of an atom is equal to the sum of the number of protons and neutrons in the nucleus of the atom. And that mass number is represented by the symbol A. So A is equal to protons plus neutrons. So in the middle, we can see a symbol for a particular element. And we're just using a generic capital E. And then on the top left, we have A, which is the mass number. And then on the bottom left, we have Z, which is the atomic number. So this is one way to represent an element or atom of an element with a particular number of protons and a particular number of neutrons. So let's look at an example, and here we have the element fluorine. And on the left-hand side, we have how fluorine is typically depicted on a periodic table. So we have the element symbol F, followed by the name, and then there's a couple of numbers on the top and the bottom. And then on the right-hand side, we have the same symbol that we saw on the last slide. We have a capital F for fluorine, and then we have 2 numbers, 19 and 9. And based on the information given above, what is the atomic number of fluorine? So you should have answered 9. So again, the atomic number is on the bottom left next to the element symbol. And because the atomic number of fluorine is 9, that means that fluorine has 9 protons. But additionally, you'll notice in the symbol on the left-hand side, which is what we would typically find on a periodic table, the atomic number is listed right above the element symbol. And that's pretty standard for periodic tables. So if you're ever in doubt about how many protons an element has, you can always look above the element symbol to find the atomic number, and that will give you the number of protons. Now, using the same information, what is the mass number of fluorine? So you should have said 19. So 19 is the mass number, and that is also the number of protons and neutrons. So remember that the mass number is equal to protons plus neutrons. And in this particular example, we have a mass number of 19, and we have 9 protons. So we're really just setting up an equation here to help us determine how many neutrons there are. So in this case, if we subtract 9 from 19, we can see that this atom of fluorine has 10 neutrons. Now, at first glance, it might look like the mass number is listed on the periodic table, but that's not actually the mass number. The periodic table does not show mass numbers for an individual atom. It actually lists a weighted average mass for a collection of atoms. So that number 19 on the periodic table is not the mass number. It's a weighted average of masses. And that brings us to isotopes. So isotopes are atoms that have the same number of protons in the nucleus, but different numbers of neutrons. So the number of protons in an atom is going to define or identify what it is. So the number of protons for a particular element will never change. But the number of neutrons can change. It can be different depending on which atom in particular you're looking at. So down below we have the example of chlorine, and chlorine's element symbol is Cl. And there are actually two isotopes of chlorine that are very abundant in nature. So in the first example, we have chlorine with a mass number of 35. And in the second example, we have chlorine with a mass number of 37. Now down on the lower left for each of these isotopes, the number of protons, or the atomic number, is exactly the same, because remember that the number of protons defines an element. So now we can take the difference between the mass number and the atomic number to find the number of neutrons. So I'm just going to make some room here. So if we take the difference between 35 and 17, we end up with a value of 18. And that would be the number of neutrons for that particular isotope of chlorine. And then if we do the same on the right-hand side here, we would get a value of 20. And so that's the number of neutrons for that particular isotope of chlorine. Now, you'll notice that this number listed on the periodic table for chlorine is not exactly 35 and it's not exactly 37. So again, that number is not a mass number for chlorine. It's going to be a weighted average of all of the isotopes of chlorine. So we'll talk about that in a bit. But first, let's talk about electrons. So previously we said that protons are positively charged and electrons are negatively charged. And all of these isotopes or atoms that we're looking at are electrically neutral. So that means that we need to have the same number of electrons as protons. Or another way of saying that is we need the same number of positive charges and negative charges. So when we're trying to determine how many electrons are present, just look at the number of protons. So all isotopes of the same element will have the same number of electrons. And then remember that neutrons are neutral, so we don't have to worry about that here. Now, there's another way to represent, or there are different ways to represent isotopes. So one example is the symbol we've already seen. So in this example, we have the element nickel. And nickel's symbol is Ni. And then on the lower left, we have the atomic number, which is 28. So that means that we have 28 protons. And that's true for every atom of nickel. Every atom of nickel will have 28 protons. And then the mass number for nickel is in the upper left, and that is equal to 60. But remember that the mass number is equal to the number of protons plus the number of neutrons. So 60 is equal to 28, the number of protons, plus neutrons. So we can take the mass number and subtract the atomic number, and that will give us the number of neutrons for this particular atom of nickel. And we should find that that is equal to 32. So there are 32 neutrons in the nucleus of this isotope of nickel. Now there is another representation for an isotope, and that involves just listing the name of the element and then putting a dash next to that, followed by the mass number of the isotope. So for nickel, for instance, we could just write out the name and then dash and then put the mass number, which for our previous example was 60. So as another example, let's say that we have magnesium 26 as our isotope. And if we want to write it in the original form that we saw, we would put the element symbol, which is Mg, and then in the upper left, we would put the mass number, which is 26. And then below that, we would put the atomic number, which if we look on the periodic table, above the symbol for magnesium is a number 12, and that's the atomic number. So we can always find that on the periodic table. And in fact, sometimes chemists will just write the mass number and leave out the atomic number because the atomic number is very easy to find. And it's always the same for magnesium. Now, I also wanted to talk about relative masses. So last time I did sort of talk about these, but remember that atoms and molecules are really, really small. We said that the diameter of an atom is on the order of 10 to the negative 10th meters. Now, additionally, their masses are really, really small. And last time we saw table 2.3, where the mass of a neutron, for instance, is 1.67 times 10 to the negative 24th grams. And that can be inconvenient for measurements or calculations. So instead, we can use relative masses. So the relative mass of a neutron is 1. And that's much easier to use than the mass in grams. So relative masses are comparisons of actual masses to each other. So in that same table, if we look at the mass of a proton, it's exactly the same as the mass of a neutron. So its relative mass is also 1. But then if we look at the mass of an electron, it's much, much less than the masses of the proton or the neutron. So its relative mass is actually 1 over 1,836. Now, as another example, if an object had twice the mass of another object, their relative masses would be 2 to 1. So relative masses are much easier to use. And you might have noticed that little symbol U next to the relative mass. That's referring to an atomic mass unit. And an atomic mass unit is used to express the relative masses of atoms. And this is actually defined as 1/12 the mass of a carbon-12 atom. So a carbon-12 atom has a relative mass of 12 U. So down below we have the isotope symbol representation of a carbon-12 atom. So the symbol for carbon is capital C, and then the atomic number is 6. So that's also equal to the number of protons. And then the mass number is 12. And remember that that is equal to the number of protons plus the number of neutrons. So if we had an atom with a mass equal to 1/12 the mass of a carbon atom, or a carbon-12 atom, then that would have a relative mass of 1 U. And 1 U is actually equal to the mass of a proton or the mass of a neutron. Now, if an atom had a mass equal to twice the mass of a carbon-12 atom, that would have a relative mass of 24 U. Now, the mass number, again, is going to be different from the atomic weight of an element. The atomic weight of an element is the relative mass of an average atom of the element expressed in atomic mass units. So when we have a sample of carbon, for instance, carbon isn't just made up of carbon-12. So on the last couple of slides, we saw that 98.89% of naturally occurring carbon is carbon-12. But we can also have, for instance, carbon-13 or carbon-14. And so both of those particular isotopes of carbon have more neutrons. And their masses, as a result, are a little bit larger. So atomic weights are the numbers given at the bottom of the box containing the symbol of each element in the periodic table. So if you look at the periodic table, there should be numbers listed below each element symbol. And those are the atomic weights. And again, that's going to be an average mass of a sample of atoms. So if we had a sample of carbon atoms, so let's say we just had a box full of carbon atoms, 98.89% of those atoms would be carbon-12. And then the rest of that percentage, so let's see, that'd be 1.11, if I'm doing my math right, so about 1%, would consist of carbon-13 or carbon-14. And so if we take the average mass of all of those different isotopes of carbon, we're going to find that the atomic weight for a sample of carbon is a little bit above 12 due to the fact that there are some heavier isotopes of carbon. So again, many elements occur naturally as a mixture of several isotopes. And down below, we have those same carbon isotopes that we just talked about. So there's carbon 12, carbon 13, and carbon 14. And again, the atomic weight is the average mass of the atoms in the isotope mixture. So down below, we can see that carbon 12 has 6 protons and 6 neutrons, and that it is naturally abundant and has a relative abundance of 98.9%. So 98.9% of all carbon atoms have 6 protons and 6 neutrons. And then carbon 13 atoms have 6 protons again, because remember, protons define the element that you have. But carbon 13 atoms have 7 neutrons. So they are a little more massive than carbon 12, but their relative abundance is only 1.1%. So very, very few carbon atoms have 7 neutrons. And then carbon 14 atoms have, again, 6 protons, but 8 neutrons. So they're even heavier than carbon 13. And they are not very abundant. So carbon 14 atoms exist less than 0.1% of the time. Now, a practical way of determining the average mass of a group of isotopes is to assume that the group consists of 100 atoms, and then we'll use the natural abundance of each isotope, or the percentage of each isotope, to represent the number of atoms of each isotope present in the group. So let's actually go over an example where we calculate the average or atomic weight of an element. So if we use percentages and the masses of each isotope to calculate the atomic weight, we'll end up with this equation, where atomic weight is equal to the sum of the isotope percent times the isotope mass over 100. So for instance, if we wrote this out, we would have the isotope percent for our first isotope times that isotope's mass, and then we would add the next isotope percent times the next isotope mass, and then we could keep going depending on how many isotopes are present. And then we just divide that by 100. So as an example, boron consists of 19.78% boron 10 with a mass of 10.01 U, so those are atomic mass units, and 80.22% boron 11 with a mass of 11.01 U. So let's start by making a little table. So boron 10 has a relative abundance of 19.78%. And its mass is 10.01 U. And then boron 11 has a relative abundance of 80.22%, and its mass is 11.01 U. So if we looked at a sample of boron, for instance, Let me use a different color to fill in the top. About 80% of the boron atoms here would be boron 11. And then about 20% would be boron 10. Now, those atoms would actually all be mixed together. They wouldn't be separated like that. But that's just to give you an idea of the percentage of each boron isotope. So now let's calculate the atomic weight for a sample of boron. So again, we're going to take the percentage for our first isotope, which is 19.78, and then we're going to multiply that by the mass of that isotope, which is 10.01 U. And then we'll add the next isotope's percentage multiplied by the mass. And then we're going to divide the whole thing by 100. So for our first number there, if we multiply 19.78 by 10.01, we get 198.0 U. And then for the second set there, we get 883.2 U. And then we'll divide that by 100. So our final atomic weight is 10.81 U. And if you look at a periodic table and find boron, boron is kind of at the top in the middle. And if you look underneath its element symbol, you should see the value 10.81, and that is its atomic weight. So what's really great about problems like this one is you can always double check your answer by looking at the periodic table, because the atomic weights of each element have already been determined. And then here's that answer slide again. So if you want to look at this later on, you can. And next time, we're going to talk about molecular weights. So we're going to start adding together the masses or weights of different elements in order to find the overall weight of a molecule. So I will see you in the next video.